Okay, let's make a start then on the production of X-rays. Now, what I would just like to say is that we could probably teach X-rays inside 1 hour, the whole thing, but I've deliberately split it into 2 bits to keep them physically separated. The production of X-rays involves some explanations that are reasonably similar but different to the absorption of X-rays that we will study next lesson. And what I need you to be very clear in your head is that the 2 pathways that we discussed today about the production of X-rays, you need to keep those completely separated in your head to the absorption of X-rays that we will discuss next lesson. Okay, with that little warning, off we go. Okay, so just in case you have forgotten from the waves topic, where you brushed against the EM spectrum, what are X-rays? They are a type of electromagnetic radiation. They do have a very high frequency, and therefore from your photons topic, you can convert that high frequency into a high photon energy. And that high photon energy is what makes X-rays dangerous. I need you to try to fix those numbers in your head. You're unlikely to get a question that says, what are the wavelengths of X-rays? But you will be doing calculations in which you end up with the wavelength of X-rays as your answer. And I need you to be able to do a common sense check to see if you're right or not. The wavelengths that are on the screen are actually fairly similar to the wavelengths of gamma rays, but the difference between a gamma ray and an X-ray is not actually the wavelength, it's the origin of the 2 different types of wave. So we call them X-rays when they are produced by charged particles rapidly accelerating or decelerating. So in our case, we're going to produce X-rays in a hospital X-ray machine using electrons, and we're going to make them go very fast, and then we're going to make them go very slow. And as they decelerate, they're going to transfer away their kinetic energy in a method that we'll talk about in a second. And that loss of kinetic energy will eventually be released from the machine as photons of X-rays. Gamma rays, on the other hand, you might remember, are produced in nuclear decays as part of the radioactivity topic, actually, which should be familiar to you from GCSEs. So similar wavelengths for both of them, but one is the acceleration or deceleration of charged particles. The other is nuclear processes. Okay, so let's have a look at how we produce X-rays in an actual hospital X-ray machine. So this is a very, very, very simple schematic of the inside of an X-ray machine. So if you've ever had an X-ray, you will know that there is a big box on an arm or a kind of pole that they can move around. And inside that box is what you're looking at on the screen now, or a simplified version of it. So on the left-hand side, what you've got there is an electric circuit that is effectively a light bulb. Now, you should be familiar with this concept from when you studied the electron gun as part of your electricity topic. Do you remember the very large glass light bulb-like device that was attached to a 5,000 volt power pack, and you saw a beam of electrons landing on a phosphorescent screen? This is just a very large version of that technology. So that's a low voltage wire that's being heated up. And what that's going to do is provide a hot metal that means that the electrons in that hot metal have got a lot of kinetic energy and almost enough kinetic energy to break free of the lattice of positive ions that are attracting them and keeping them in place. Across on the other side of the X-ray machine, there is a very large lump of metal, which is often tungsten. Okay, so we are going to be firing electrons at the tungsten. So we need the electrons to have a reason for traveling from the the light bulb filament to the tungsten. So what we're going to do is turn the whole thing into an electron gun. So we're going to attach a kilovolt supply between the tungsten, which is going to become an anode, and the hot filament, which is going to become the cathode. Depending on what you want to do with the X-rays, you would choose a voltage somewhere between 50,000 and 200,000 volts. So these are not messing about. The electron gun we have in the lab is only 5,000 volts. Okay, so what's going to happen is when we turn that on, the positive anode is going to attract the electrons from the negative cathode, and those electrons are going to accelerate across that gap. Next year, we will study electric fields, and we will look at exactly how an electric field is set up in that gap and how that electric field provides a force that accelerates the electrons, and we'll look at the energy that is actually transferred. So that's all in your future when we study electric fields. But for now, I think you can appreciate that if you put a negative electron next to a very, very positive object, the negative electron is going to accelerate towards the positive object. When the electron collides with the tungsten anode, it basically produces a shower of X-rays, and those X-rays will be emitted in all directions, but the casing is shielded, and there is just a small window in the bottom of it. And if you've ever had an X-ray machine hover over the top of you, you'll have seen the window. There's usually a light bulb inside it, which shines visible light through the window so that the person operating the machine can see where the X-rays are going to land by looking at where the visible light lands. That's the basic principle, but I think you would agree that the picture on the screen is more GCSE than A-level, so we need to add some detail to that. So one little bit of detail that I would like you to make a note of is that the anode is tungsten. You should know the name of the material. And the process by which the electrons are taken from the hot cathode is called thermionic emission. It's emission by heat, thermionic emission. Okay, let's add a little bit more detail. Okay, so 50 to 200,000 volts. I've said that. And that. The window that is on the bottom is of variable size. If you are imaging somebody's chest, you're going to need a large amount of X-rays. But if you're imaging someone's little finger, you're going to need a very small amount of X-rays. What we don't want to do is focus the X-rays. We don't want to take all of the X-rays that were destined for a chest and take all of those and focus them down into a narrow beam to X-ray a little finger. What we want to do is just get rid of some of the X-rays. So all we do is make the window smaller so that fewer of the X-rays leave the machine, because what we don't want to do is unnecessarily expose the patient to X-rays. We only want to X-ray the part that we are concerned has a problem with it. Okay, here is a fact that you should be aware of. It is often examined just as a throwaway 1 or 2 mark question. So just be aware of the fact that this is incredibly inefficient. We'll talk about the process that is inefficient in a minute, but the process itself of producing X-ray photons is very poor in terms of its rate of conversion. So less than 1% of the kinetic energy will be converted into photons. So the other 99% of it, which is considerable given that the current of electrons is huge, traveling across that 200,000 volt gap, that 99% just heats up the tungsten. Now, if we were to just have a solid tungsten block, it would melt the tungsten with continued use. So what we do instead is to make the tungsten block disc-shaped. You can see the cross-section of it in the picture. So it's a spinning disk, actually, mounted on an axis here. So it rotates about this axis, round and round and round it goes. And what that means is that the part that's being heated up keeps changing. Now, the disk is spun pretty fast, actually, because the tungsten would melt fairly quickly if left in one place. So we spin it fairly quickly. And often, if you're using high voltage and the X-ray machine is in constant use, it's often not enough to simply move the tungsten out of the way to put a new piece in its path of the electrons. We might actually cool it as well. And so there might be some kind of coolant system flowing inside the tungsten that's attempting to remove the heat as quickly as it arrives. Okay, if we were in class, I would subject you to an 8-minute documentary film from the 1940s. 8-minute documentary films from the 1940s are always amusing to watch, simply for the way that they speak. This presentation is already on Google Classroom. So at the end of this lesson, if you want to download it and follow that link and watch the video, you can. It's just a little aside, a bit of fun. It's not examinable. But William D. Coolidge was the person who invented the original concept of the X-ray machine. And you can watch him explain it to the public at large in his own video. Like I said, bit of an aside. Okay, we are going to talk now about the two methods by which X-rays are produced as the electrons interact with the tungsten. One more time, next lesson on Wednesday, I will teach you about 4 different methods for how electrons interact with the human body. What I would like you to do, if you can, is to keep the 2 lessons separate in your head. Okay, let's talk about this one first. So, type number 1 is called Bremstra Lung, which is German for braking radiation. Not radiation that breaks stuff, but radiation that is produced as electrons decelerate, as they slow down, as they break. Okay, so we don't study Maxwell's equations of electromagnetism as part of your A-level. They're a university level topic. But the Maxwell equations is a branch of physics that describes how electromagnetic radiation is produced. And it states quite clearly the prediction, which has been observed very, very many times, that when charged particles accelerate or decelerate, they will emit electromagnetic radiation. This isn't in question, but it isn't on your A-level topic, so I'm just sharing it with you now. So what's going to happen is that electron was traveling in a straight line from the X-ray machine, as indicated by the black arrow on the screen. But as it reaches the tungsten, eventually it is going to travel past a tungsten atom, and with it the tungsten nucleus. And as the electron travels past the positive tungsten nucleus, there is going to be an attraction. And what that is going to do is make the electron swerve. It's going to change its direction. It's also likely to slow down as it travels close to the nucleus. And what happens as it alters its velocity, as it travels past the nucleus, is that Maxwell's equations will predict that it will produce some energy. So it began with an energy E1. After it has passed past the nucleus, it will have an energy E2. And if you work out the difference between those two, you'll find that the electron has lost an amount of energy, and that energy via E equals HF will have been emitted as a photon. And we make sure that the energy of the electron coming in and the interaction with the tungsten is such that that change in energy produces photons in the X-ray spectrum, which is one of the main reasons why we choose tungsten as a target. because the electron is constantly changing by different amounts of energy, as different electrons pass by different nuclei at different distances, at different angles, with different amounts of interaction, every single electron that enters the tungsten and interacts with a tungsten ion will undergo a different change in energy. And that change of energy will form a continuous variable. That change of energy can be any number at all. And therefore, the frequency of the emitted photon and the energy of the emitted photon can be any energy and frequency at all, which means that Bremstra Lung produces, or Bremstra Lung is, a continuous spectrum of radiation. It doesn't produce specific values. It produces a continuous distribution of values. So if we were to draw it on a graph, as we will in a moment, it produces a continuous line, a kind of bell-shaped curve. It doesn't have specific values that you would see coming out. So it'll be a continuous distribution. Okay, the second way that the electron can interact with the tungsten is to not interact with the tungsten's nucleus, but to interact with the tungsten's electrons. Now, to be fair, there is a lot of overlap here between how the electron beam interacts with the tungsten's electrons and how the X-ray beam is going to interact with the patient's electrons. However, I need you to appreciate that what we're talking about in the production of X-rays is a matter particle, an electron, interacting with electrons, whereas on Wednesday we're going to be talking about photons interacting with electrons. So although it's going to sound very similar, the processes are different, and I need you to, one more time, keep the two separated in your head. So the beam of electrons from the cathode is going to enter the tungsten anode, and some of those electrons can interact with the tungsten's electrons. And the process of that is not something that you need to understand in detail, but you can understand in principle that a negative electron is going to repel a negative electron. And as the incoming beam of electrons passes through the orbital electrons of the tungsten, you can imagine a situation in which there is repulsion between a pair of electrons. And what that can do is to cause the tungsten's electrons to become promoted into a higher orbital, a higher energy shell than otherwise it would be. So the beam will fire through the tungsten. The tungsten's electrons will become excited and go up into higher energy orbitals. And then after the electron has passed past, as we have discussed many times in the nuclear topic, the natural state of things is to decay and lose energy. So these excited electrons will fall back down into lower energy states, which should be familiar to you from chemistry, because you'll have studied excited states in chemistry as well if you've taken an A-level in chemistry. So the arrows on the diagram represent the paths that electrons that have been excited into higher orbitals could decay via. So if you look at the ones labeled K, you could find two different electrons falling down into the ground state. The one labeled K alpha has fallen down from the first excited state, the first shell above the ground, whereas the one labeled K beta has fallen down from the second shell. So if it was a ground state electron that got excited up, it might have been excited up into the first shell above ground, or the second shell above ground, or the third, or the fourth. And when it falls back down again, whether it fell from the first shell to the ground or the second shell to the ground will release different amounts of energy and therefore different frequencies of photons. Likewise, an electron might have been excited from the first shell above ground up to the second or third. Those are the ones marked L. And then they can also fall back down to the ground state as well, which aren't labeled by arrows on the diagram. What you can see is that there can be transitions between any pair of shells, and every single pair of shell, excited shell to what it's going to decay down into, has a different energy separation, and by E equals HF will produce a different value of the frequency of the emitted photon. There are only a finite number of pairings. It can be considerable in a large atom like tungsten, but there are only a finite number of these values of HF that can be produced. And so whereas the Bremstra Lung was a continuous spectrum that could produce any value of frequency and any energy of photon, these type of X-rays are known as characteristic X-rays because they are characteristic of the tungsten. They are matched to the pairs of shells that the electrons in a tungsten atom occupy, and there are only so many pairs of shells. So there will be a few dozen characteristic frequencies of X-rays that can be produced by the tungsten's own electrons as they decay back down from their excited states. So if we turn an X-ray machine on and we have a look at what comes out, this is the kind of picture that you would get. So it is always drawn as wavelength rather than frequency or energy, which is slightly unnecessary, I think, but it's just the way it's always been done. So different curves for different settings on the X-ray machine. So you remember that we would generally start higher than this for a machine that is going to be used for imaging humans. The highest curve here is 25 kilovolts. We would generally start at 50 and move up to 200, but it gives you the idea that as the accelerating voltage of the X-ray machine, as that's increased, the peak of the continuous spectrum gets to shorter and shorter and shorter wavelengths. And so we would tune the machine so that the peak was falling in the region of X-rays that produces the best image of the patient. And by trial and error, that is where the range of 50 to 200 kilovolts has come from. And we'll talk about how it interacts with human tissue and why that range is where it is on Wednesday. You can see layered on top of the curves there, you can see the K alpha and the K beta, an extra spike, an extra production of X-rays, higher intensity there. So those frequencies of X-rays are able to be produced by Bremstra Lung, but they're also produced by the characteristic radiation as the electrons of the tungsten decay from excited states. So there's extra production of the characteristic X-rays, and that's why there's extra spikes layered on top of the continuous spectrum. So just a heads up, common exam questions are to give you a picture like that and to just ask you why are the spikes on the curve, or to identify any interesting features of the graph, and you would highlight those spikes and attribute the general curve, the general shape of the curve, to the Bremstra Lung, the continuous spectrum, but the spikes to the characteristic X-rays produced by decaying excited states of electrons in their orbitals of the tungsten atoms. Okay, I'm going to come back to that graph in a second, but just to note, to be explicit about the note, that we want the X-rays because they pass through stuff, but they don't pass through everything. So you are well aware that the X-rays pass through soft tissues, but they don't pass through bones. This is why we like X-rays. Visible light doesn't pass through soft tissues. We can't use visible light to look inside people, which is probably for the best. But X-rays can, and it is this ability to pass through some materials and be absorbed by others that makes X-rays ideal for what we want to do. However, it's important that you understand from this very first lesson that in order for a patient's tissues to absorb X-rays, they have to have a process by which they can absorb the X-rays, and that process, as we'll see on Wednesday, is generally damaging. And what that means is that, yes, we want to expose the patient to enough X-rays that they are going to have an image of their insides produced, but we don't want to overexpose them to X-rays unnecessarily. So it's important that we make sure that the spectrum that we expose them to is just enough to produce the image and no more. So the issue here is that some of these X-rays are going to be really great at producing images for us, and other X-rays down here are not going to be useful to us. And that is a small problem if you're a patient and your doctor is about to say, let me just shine some X-rays on you, because you'd quite like them to have removed any excess X-rays. So try to get some of these numbers lodged in your head. Again, you will never receive a question where you are asked to reproduce these numbers, but you might be given a graph where you have to identify aspects of the graph, and you'll just make your life easier if there are numbers that you can aim for. So what you want to appreciate is that these X-rays here, these short wavelength X-rays from about 1/100th of a nanometer to about 1/10th of a nanometer, these really, really short wavelength, high energy X-rays, those are the ones that are going to pass through the soft tissue and are going to be absorbed by the bone. It's these really short wavelength X-rays that are going to produce the image for you. But the longer wavelength X-rays that are produced by the machine, from about 1/10th of a nanometer up to about 10 nanometers, these longer wavelength X-rays, so on the curve, these ones down here, they are not going to contribute to the image. And the reason they're not going to contribute to the image is because they're going to be absorbed by the soft tissues as well. So they are not going to come out of the other side of the patient. They are not going to be detected by a detector. They are not going to add to the image at all. And yet you've just ionized your patient unnecessarily by these longer wavelength X-rays. So these longer wavelength X-rays that are absorbed by soft tissues are often referred to as soft X-rays. The other ones that go straight through are referred to as hard X-rays. The soft isn't from soft tissue. It's just a terminology from electromagnetism. Higher energies tend to be hard X-rays. So it's not ethical to bathe the patient in soft X-rays. We need to remove those before they come out of the machine. So all we do, if we just go back to the original picture, we just are going to put something across that window there. So rather than it just being a gap, we're going to find a piece of material that also absorbs soft X-rays, but allows hard X-rays to go through. So it probably wouldn't be nice to use a piece of human to do that. But luckily for us, aluminium has the same properties. So if you are ever X-rayed in the future, just glance up at the window that the X-rays are coming out of, and you might be able to see evidence of a material across the window. And that is just to prevent the soft X-rays from leaving the machine. They're absorbed by the aluminium sheet, and that means that only the hard X-rays are emitted, which sounds a little bit dangerous because they are the more dangerous X-rays, but they're the ones that are going to go straight through the patient's soft tissues. So those are the ones that we want. The phrase that you need to be aware of is that this is called hardening the beam. So placing some absorbent material across the window of the X-ray machine to remove the soft X-rays is called hardening the X-ray beam. And that is actually it for production of X-rays. So if I just highlight the key parts for you that I want you to be clear on, I need you to have a rough idea of the wavelength of an X-ray. I need you to understand that it is produced by decelerating electrons. A rough idea of the fact that an X-ray machine is an electron gun with, try and get this 50 to 200 kilovolts in your head as the operating voltage. That the anode is made of tungsten. That it's very inefficient, and so that we need to spin and often cool the tungsten. But there are two methods of producing X-rays. Bremstra Lung, which is a deceleration of electrons as it passes the nucleus, and that produces a continuous spectrum. And these characteristic X-rays as the electron beam interacts with the electrons of the tungsten, and that produces spikes that are characteristic to the electron orbitals in the tungsten atoms. And that finally, we only want the shorter wavelength X-rays that are produced by the machine. And so in a process called hardening the beam, we remove the soft X-rays.